Our topic, our next topic, is the definite integral. And I'm going to ask you to do the impossible and forget everything you know about snakes so far. You've never seen a snake before. Okay? And the reason is that what we're going to do now is going to seem at first completely, but completely unrelated to indefinite integrals. And the only thing that's going to be similar is those snakes. Okay? The notation. And the reason for the notation is only going to be revealed later this week. Okay? So please forget everything you know about snakes. We're starting something completely different. And here we go. Our motivation, the question we're interested in now, is the following. Suppose you have a function. Here it is, some function. Let's be original and call it f. And we're looking at the function on a specific interval, namely the interval between a and b. And what we want to know is the following. What is the area under the graph of the function? That's the question. What is the area under the graph of the function? For simplicity, I'm going to assume the following. I'm going to assume the function is positive. We're going to drop that assumption later. I'm going to assume the function is continuous. We're going to drop that assumption later. The only crucial assumptions are that the function is bounded. It can't go to infinity anywhere, in which case it clearly the area requires some further definition. Something is not clear when the function is not bounded. So it's going to be a bounded function on a finite interval. Okay? Those are the two crucial assumptions. The other assumptions are just for the sake of simplicity for now. Do I know to calculate areas in general? Yes. What areas do I know how to calculate? Right. I know squares. I know rectangles. If I try real hard, maybe I can remember circles. Right? There's a pi showing up there. Right? Oh, I know triangles. They're 1/2 of the rectangles. Right? So that's the kind of things I know. This is not a square. It's not a circle. It's not a rectangle. I'm lost. Okay? So here's the idea. The idea is the following. Let's take this interval from a to b and break it into little intervals. Not necessarily following any pattern, just any little intervals you want. So this is the x-axis, and I'm going to call these points I chose, I'm going to call them x1, x2, x3, x4. Maybe 4 is enough for now. Okay? I chose 4 random points. Okay? On these points, I'm going to draw lines going up till they hit the graph. Good. Now, using a different color, so what I just did formally, I'm going to write everything in a minute with all the formal definitions. This is called a partition of the interval AB into little parts. That's why it's called a partition. Now I'm going to choose points in each of these little new partial intervals. So I'm going to choose a point here, and I'm going to choose a point here, not necessarily at the center of the interval. Maybe here, maybe here. I can choose the end point, and here. So in each of the 5 intervals I got, I chose a point, and I'm going to call these points using the letter C. So this is going to be C1, C2, C3, C4, and C5. I hope this isn't too small and you can actually see it. Good? Now I'm going to calculate the value of the function at these orange c's. So f of c1 is going to be here, f of c2 is this value, f of c3 is this value, f of c4 was the endpoint, it's this value, and f of c5 is this. Good? And now I'm going to take rectangles whose bases are these parts from the partition. So I have the width, and the length, or the height, is going to be determined by this value here, the value at the orange point. So I'm going to get a rectangle like this, and a rectangle like this, and a rectangle like this, and one like this, and one like this. Is it clear what I just did? So what did I get? I got a bunch of rectangles, in this case 5 of them, and the area of these rectangles, the sum of the areas of these rectangles is, well, not exactly the area under the blue graph, but it's an approximation of the area under the blue graph. Do you agree? Why is it not exactly? Because there are obvious errors here. So there's this area here, which I'm going to count, but it's above the graph, right? And there's this area here, which I'm not going to count, but it is under the graph. Do you see that? And here there's a wild error. There's all this area, which I'm going to count when I add up the areas of the rectangles. But this area is clearly not under the graph. This is the graph. Do you agree? So there are errors. It's not an accurate approximation. It's an approximation. Can I make it better? Can I do better? How can I do better?
More rectangles.
Right. Use more rectangles. Okay? Make the partition more delicate. Okay? For example, let's take this. This rectangle, the fifth one, is the one that introduces the biggest error here. Let's break it in two. Let's add another point here. Let's call it x5. That will add this line here. And now let's add another. So this is going to become C6. And I'm going to add a point here. This is going to be C5. This is the value at C5. So now this rectangle is going to be this one. And here I'm going to get this rectangle. And all this error here is gone. Okay? Is it clear what I'm doing? I'm going to erase it on the drawing. So all of this is now gone. You're gone. Don't try to stay. Now this is the picture. It's still not accurate. It's an approximation, but it's way closer. Do you agree? And I can do better. I can take any rectangle, break it in two, and the errors are going to get smaller and smaller. Do you agree? So the sums of these rectangles are called Riemann sums, named after a mathematician named Riemann, whose role in differential and integral calculus is very important. So let's write what they are, these sums. So it's a sum, and I'm going to introduce this sigma notation. Do you know what the sigma notation means? Sum. So sum, I equals 1 to n. N is the number of rectangles I have. And what are the areas? It's the length of the ith interval. So I'm going to call these, I'm going to call the length of the first interval delta x1. This is standard notation, that's why I'm using it. And the second interval is going to be delta x2. Okay, and so on. So delta x1 is just x1 minus a. Delta x2 is x2 minus x1. It's the width of the rectangle, right? And what's the height? F of the orange point. So this sum, the sum of the rectangles, is f of ci times delta xi. This is called a Riemann sum. Do you agree? Can everybody see that this sum here is precisely the sum of the areas of the rectangles, which is an approximation for the area under the graph? Good? Everybody? Okay. And am I ever going to get, so I'm going to make n bigger. Now n is 6, right? I have 6 intervals. I can make n 60 or 100 or 1,000,000 or 1,000,000,000 or a Google. Do you know what a Google is? Big number. Is it ever going to be precisely the area under the graph? No, but we know something else in this course. We know limits. And the statement we want to make somehow formally is that in the limit, and we're going to have to formalize this, but an informal way of saying it is take n to infinity. So when n goes to infinity, you're breaking it into more and more and more and more and more rectangles. In the limit, this is going to converge to, let's call it I temporarily, which is, I stands for integral, which is the area under the graph. Area under the graph. And this limit thing is not precise, and I'll explain why and how to make it precise in a minute. But for example, you can see that it's not precise by saying the following. So what does it mean taking n to infinity? It means breaking the interval, making the partition more and more delicate, taking breaking the rectangles again and again and again and again, right? But suppose I just stick to this one and take 1/2 of it every time. I'm not going to get any, I'm never going to take care of these errors, right? So just by taking more and more rectangles, that's not enough. I have to make sure I do it all over the interval, right? So just this statement is insufficient. Do you agree? But this is the idea. This is the idea of what we're going to formally define now. So the area under the graph, which I denoted by I temporarily, it's going to be denoted by a snake, you know that, is going to be, in some more precise sense, the limit of Riemann sums, which are sums of areas of rectangles obtained by taking a partition of the interval and choosing points where to evaluate the function. Clear? So this is kind of the introduction. This is what we want to do. Everybody with me? Questions? Okay, so let's start making all of this formal. So everything I'm going to do, keep peeking at this drawing and making sure that everything corresponds to your intuition from this drawing. Okay, that's what it should be. So, definition. A equals x0 less than x1 less than x2 less than ... less than xn, which is b, is called a partition of the interval a, b. Clear? It's a choice of points where you force x0 to be the a and xn to be b, and then you choose all these intermediate points in ascending order. That's a partition. Clear? That's exactly what we did in the drawing. A partition of AB denoted by P. That's the letter we're going to use, P for partition. Delta xi will denote x I minus xi minus 1 in the index. So the ith point minus the I minus 1th point, that's the length of the ith interval. Clear? No, I minus 1 here. Okay, it's delta x5, the length of the fifth interval in the partition, is x5 minus x4. Okay, the first one is x1 minus x0, and x0 was a. Clear? Okay. So, another definition. Lambda of P is going to denote, this is the Greek letter lambda, okay? If you know Hebrew, don't confuse it with Hebrew letters. Greek letter lambda is going to be the maximal between the delta xi's. The widest of the rectangles. Okay, the biggest interval in the partition. Clear? That we're going to denote by lambda of P. Okay, and here's the next definition. I'm just formalizing everything we said. Let P be a partition of AB, and let F from AB to R be bounded. That's the only condition that I'm going to strictly enforce throughout the discussion of definite integrals. The function has to be bounded. Okay? Everything is going to fit in nicely with the intuition whenever it's continuous and positive, but the definitions don't require that, but they do require it to be bounded. Choose points Ci, each point in the interval xi minus 1 xi. So those are those orange points. Then, sigma I equals 1 to n, f at Ci delta xi is called the Riemann sum corresponding to F, P, and the CIs. So it depends on the function, it depends on the partition, and it depends on the choice of the CIs. Okay? Change any one of those pieces of data, you get a different Riemann sum. Good? That's for the next definition, which is where we're going to stop today. So I want to define, and we'll pick up from here next time. So remember, F from AB to R is bounded. We say that F is Riemann integrable Riemann integrable on AB if, and what I want to write here is somehow formalizing the statement, the limit of the Riemann sums approaches some value, which we called I. So let's write that. If there exists an I is going to be the candidate for the integral, okay, such that, and now this is going to look terrifying, wicked. It's going to somehow hide the definition of the limit, but it's going to be much more complicated. There are going to be many more quantifiers for everys and exists. Okay? Because we somehow have to take care not just of n going to infinity, but somehow saying that we do it simultaneously on all the little subintervals. And that's why it's going to look scary, but don't be concerned about that. We're not going to work directly with this definition. I still want to write it precisely once. Okay? We're going to work with the idea of the Riemann sums approaching the integral. So if there exists an I such that for every epsilon there exists a delta, so far this should look familiar, such that for any p, for any partition with lambda of p less than delta, meaning if you take a partition where the fattest rectangle is at most delta, then the Riemann sum corresponding to that partition, f of ci delta xi, minus the limit, the integral, is less than epsilon. And this should happen for any c1, c2, dot, 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 cn, for any choice of these ci's. This definition is a mouthful. It's maybe the mouthfulest definition of this course. We're going to stop now. Next time I'm going to write this definition again on the board, draw the drawing again, and decipher it for you. But it's a good idea to look at it again on your own before next time. Come prepared. It's a good practice of being able to absorb things like this. So we're going to continue from this definition and then write more theorems next time, and see how we actually calculate integrals using Riemann sums, and then how we calculate integrals in more sophisticated ways, and ultimately the fundamental theorem of calculus, which tells us how these relate to antiderivatives.